Welcome to section 0.4 about counting techniques, and we're going to talk about three things here today. We're going to talk about the fundamental counting principle, we're going to talk about permutations, and we're going to talk about combinations. The first thing, and you'll notice as we go through this, that a lot of the definitions are already written down. Now, please do write those down on your notes. I'm not going to spend a lot of time. I'm just going to talk through it a little bit and then move on to the examples. So you may have to pause the video when we get those definitions in order for you to get things written down. Okay, so the fundamental counting principle is the number of possible outcomes in a sample space. It can be found by multiplying the number of possible outcomes for each event. You're going to see here on this first page that we're going to do a ton of multiplying. Okay, and the numbers we use, right, in those spaces when we multiply is the number of possibilities we have for that particular thing, whatever that thing might be. Okay, so we're going to use counting techniques for both independent and dependent events. We're going to start first with independent events. So, for example, if there's two events, event A and event B, they do not affect each other. For example, what happens in A has no bearing on what happens in B, and vice versa. Okay, so these first four examples, we will be dealing with independent events. As we go through the problems today, you'll start to get a feel for, first of all, what's independent versus dependent. And then also, is this situation going to need, or am I going to have to use a permutation or a combination for this certain event? All right, and we'll get to those when we turn the page here. Okay, but first of all, using the counting principle for independent events. Example 1. A sandwich cart offers customers a choice of hamburger, chicken, or fish on either a plain or a sesame bun. How many different combinations of meat and bun are possible to make a sandwich? So, we're making a sandwich, and there's two things. The bun type and the type of meat. Okay, so I'm going to write down two blanks. Okay, there's a type of bun, and then there is a type of meat. Now, we're going to put numbers in those blanks. First of all, for the buns, how many types are there? Well, let's see. There's a plain or a sesame bun. So there's two types, plain or sesame. And then for meat, how many different types of meat can I have? 3. Hamburger, chicken, or fish. So there's 3 types of meats. We multiply those together. Easy one here. 6. So there are 6 different combinations of meat and bun for our sandwich. And that's example 1. Example 2, we're moving from making a sandwich to making a yogurt parfait at Dairy Queen. When you make your yogurt parfait, you can choose one flavor of yogurt, one fruit topping, and one nut topping. How many parfait choices are there? So this time, I'm going to have 3 numbers I multiply together. Okay, flavor of yogurt, fruit topping, and nut topping. So here's the numbers we're going to use for that. For flavors, if you look in the nice colorful chart over here, we have 2 different flavors, plain or vanilla. There are 5 different fruit toppings we can use. Okay, in that middle blue section of that chart, there's 5 different fruit toppings. And then there are 3 types of nuts we can put on top. Almonds, peanuts, or walnuts. We multiply 3 numbers together this time to get 30. So there are 30 different parfait choices that we could make. That's example 2. Okay, now notice these were all independent events so far because what type of bun doesn't affect the type of meat and vice versa in example 1. All right, and then example 2, the flavor of yogurt doesn't affect the fruit we put on it, doesn't affect which types of nuts that we choose. Okay? All right, so in example 3, many answering machines, which we don't use anymore really, allow owners to call home and get their messages by entering a 3-digit code. How many codes are possible? Okay, so I'm going to have 3 blanks. And these 3 blanks are going to represent the first digit. We'll call it digit 1 of our code. digit 2 of our code, and then digit 3 of our code. Okay, so it's a 3-digit password. Okay, now, how many different numbers or different digits could be used for each number in our code, right? Well, here's the deal. There are really 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? There are 10 digits that make up every number in the world. Okay? So for each of these blanks, I have 10 choices for what could go there. Now, that 10 doesn't represent the number 10. That represents the number of choices I have for that particular digit in my passcode. Okay? Because for digit 1, I could choose any one of these 10 digits. And then I could also choose any one of those 10 digits for digit 2. And I could also choose any one of those 10 digits for digit 3. Multiply them together. There are 1,000 different codes, 3-digit codes, that we could enter. Now, number 4. Again, we're staying with passwords. Okay, but this password is going to have digits and letters, all right? So a password for a site consists of 4 digits followed by 2 letters. The letters A and Z are not used, and each digit or letter may be used more than once. How many unique passwords are possible? So this time, we are going to have 6 blanks. Okay. The first 4 are the digits. So digit 1, digit 2, digit 3, digit 4. Okay? Now, that's followed by 2 letters. So blanks 5 and 6, letter 1, letter 2. Now again, for each of these blanks, we have 10 choices for what can go in there for the digits. There's 10 different digits I could choose here, 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 or here. Now for the letters. There's 26 letters in the alphabet. There are 26 letters. But A and Z are not used. So 2 of those 26 we're not allowed to use. So we only have 24 choices for what letter could go here or here. And then we simply multiply all of that together. 10 times 10 times 10 times 10 times 24 times 24. And so now this time there are 5,760,000 different unique passwords that can be used. Go ahead and turn the page. Okay, so those were all independent events. What happened with one blank, for example, didn't affect what happened with the other. Now we're going to talk about, we're still going to use the counting principle, the fundamental counting principle, right? But now we're going to use it with dependent events. So with dependent events, the outcome of event B is affected by the outcome of event A, or vice versa, all right? They are going to affect each other. Okay, so, for example, in number 5, Sarah must take 6 different classes next school year, assuming that each class is offered each period, okay, which really, for this problem, that is kind of extra information that doesn't matter, okay? How many different schedules could she have, okay? All right, so let's say this. There's 6 classes a day, all right, traditional period, okay? So, or traditional day. So let's do this. There's going to be 6 blanks, all right? Period 1. I'll just write P1, okay? Period 1, period 2, period 3, period 4, period 5, and period 6, okay? All right, so let's say that there are only, all right, so we're not not talking about the number of different schedules based on the hundreds of different classes, okay? We are just talking about, right, there are 6 hours and there are 6 classes that she can take. Say she's limited to just 6 different classes, okay? All right, so, I don't know, let's say, for example, to help explain this, let's say she's got a math class, a science class, social studies, a gym class, an art class, and a study hall. Those are the 6 classes she has to choose from, all right? So, for period 1, it's a clean schedule. She could take any one of those 6 classes in period 1. So she has 6 choices, right? Well, let's say she wants to get math out of the way, all right? Just takes math, first out, all right? That was the one she chose, but she had 6 choices. Now for period 2, she only has 5 choices left for period 2 because she's already taken math. She don't want to take it again, right? All right, so for period 2, there are only 5 choices. So let's say she took study hall, second out. Now for period 3, there's only 4 choices. Let's say she took gym, third period. Now for period 4, there's only 3 choices. Let's say she took science. All right? Say she took science. All right, and so then there's 2 choices, either social studies or art. Let's say she took an art class. And so for the last period of the day, there is only 1 class to choose from because there's only 1 we haven't taken. So 1 choice. Multiply those together. Okay. We multiply those together. 720. Let's see where I can fit that in. There are 720 different schedules that she could take. Now, that's assuming there's only 6 different classes, right? Right? If there was like 20 or 50 or 100 different classes, for period 1 she would have had 100 choices. Then for period 2, 99, and period 3, 98, all the way down. Okay? All right, but that's an example of what a problem looks like when you have dependent events. Okay? Your numbers are going to change, right? Because your choice, all right, for each choice, we're going to eliminate 1. All right, so now one more problem here on dependent events using the fundamental counting principle. Okay? All right. A password is 4 letters followed by 1 digit. How many passwords are possible if no repetition is allowed? Okay, so what the no repetition is allowed means is, let's say in our password, the letter A is our first letter. Well, then you can't use it again, right? So let's see, 4 letters. So 4 blanks. All right, so that's letter number 1, letter number 2, letter 3, letter 4, followed by 1 digit. Okay, so digit 1. Okay, so there's 26 letters in the alphabet. So I've got 26 choices for that first letter. Now, I can't repeat letters. So for letter 2, I can't use the one I used for letter 1, so I have 1 less to choose from. Okay, and then in letter 3, I can't use either of the letters I used for letter 1 or letter 2, so I only have 24 to choose from. And then for letter 4, I only have 23 to choose from. All right, because I can't repeat what I've already used. So it's 1 less choice I have. Now for the digits, well, there's 10 digits. Got 10 choices here. We're going to multiply these numbers together. So there are 3,588,000 different passwords. Okay, now, you'll notice in number 5 here, we multiplied 6 times 5 times 4 times 3 times 2 times 1. Okay, that is what we call a factorial, or you could look at it or view it as a factorial. Okay, what a factorial is the product of all counting numbers beginning with n, with whatever number you're beginning with, whether it's 6 in that example or something else, and counting backwards to 1. Now, counting numbers, the numbers we count with, like 1, 2, 3, 4, 5, 6, like that. Okay, so For example, look at this. Here's that exclamation point, okay, which we've talked about before. So 6 exclamation point is 6 factorial. It's not like we're really excited to be writing the number 6, right? It does have a mathematical meaning, all right? It is 6 times 5 times 4 times 3 times 2 times 1, and again, that's equals 720, all right? So why are we doing this? Why are we talking about factorial here? Because in a minute, we're going to talk about permutations and combinations, and there's special formulas for those two things, which include factorials. Okay? So, let's look at example A here. All right? So, 12 factorial. All right? Watch all this. We got to write all this. So, 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I'm going to move it to the left because I ran into part B. All right? That's what 12 factorial is. All right, which is 526,901,760. Huge number. Now, your calculators do have a factorial key, and if you want to know where that is, you can come and ask me at any point. Okay, part B. So this is where people start to get fooled. Here is what B is not. B is not 15 factorial. You can't multiply them together. You have to do each factorial independent of the other one. Okay, so the 3 factorial would be 3 times 2 times 1. And then the 5 factorial would be times 5 times 4 times 3 times 2 times 1. That's how you do part B. And in the end, all right, you end up with 720. Okay. All right, so now part C. Okay, so here is where we're going to get into canceling some things out. All right, so 6 factorial. 6 times 5 times 4 times 3 times 2 times 1 divided by, okay, well, 2 factorial, let me change colors here. 2 factorial is 2 times 1. And then 4 factorial is 4 times 3 times 2 times 1. Okay, now look at the red and the green. Aren't there some numbers that match up? Remember, in a fraction, you can cancel stuff out from numerator to denominator if it's the same. And we can do that here. So look at this. 4s are going to cancel out. 3s, 2, 1. All right, so this problem ends up being a little bit simpler, all right, than what it may initially have looked like, because we've canceled 4 different digits out. So now in the numerator, you've got 6 times 5, which is 30. And then in the denominator, you've got 2 times 1, which is 2. It's 15. Our final answer. Okay, and so now the same thing would happen with D. All right, that's no different than C. I'm not going to go through and do it. Right, but C and D, same idea. Okay, you could practice D if you want. Right, and you should get 56 as your final answer. All right, if you want to give it a shot. Okay, now we're going to move on from the fundamental counting principle into what we call permutations and combinations. Now, permutations and combinations, right, they differ in the fact of whether order matters or not. So permutations of different objects taken at a time deals when order matters. Okay, so permutations, order matters. So the examples we have where order matters is like in number 7, we're awarding bronze, silver, and gold medals in a figure skating competition. Obviously, order matters. There's a difference between first place, second, and third. Right? And then, again, in 8, we have another contest or another competition where we're ordering blue, red, and green ribbons. Right? That would be a permutation because order matters. Okay? So there's 2 examples. Okay? Now, permutations has a formula that goes with it. Okay? And the issue with what's in your notes is that the formula is written incorrectly. Okay? You can see in red, I have written it, or rewritten it, or added to it with red. Okay? So change that formula in your notes to what you see there. You're going to put parentheses around the N and the R, and then the factorial is outside the parentheses. Okay? All right? So make sure that you fix, and I'll point at it, this right here. Okay? Now, n and r. N is always bigger than r or they're equal. Okay, n is always bigger than r or they're equal. R is never going to be bigger than n. They could be equal, but n will be bigger or equal. Okay, so n is always the total number of items, right? But sometimes we don't use all the items. Sometimes we only use a handful of them, and that's what r is. Okay, so our formula here, all right, let's look at this example actually. So let's look at this example. All right, the number of permutations of 7 items taken 3 at a time is represented by this, let's try that again, this right here. That P with the 7 and the 3 on either side means 7 objects taken 3 at a time using permutations. So the number on the left is n, always. Number on the right is r, always. Okay, n on the left, r on the right is alphabetical order. Okay. Now, look at what you see then to the right. So then to the right, we are using this formula for permutations. Okay? And by that, I mean this one right here, right? So n factorial, the numerator, divided by n minus r factorial. Now, again, these notes, there should be parentheses there, and the factorial there. Okay, so what you're really doing here is 7 factorial over 4 factorial, right? And coming up with an ultimate answer of 210 if you're interested. Okay, 210. So let's do a couple of these, right? So in part E, okay, in part E, I have 8 items taken 7 at a time using permutations. Okay, so let me just write below this first that 8 is our n and 7 is our r. So we're going to use our formula, 8 factorial over 8 minus 7 factorial. Okay, so in other words, this is 8 factorial over 1 factorial, which is really 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 1 factorial. That doesn't really help us, right? All right, but we do all that multiplication in the numerator and then divide it by 1 if you want. 40,320. Okay, 40,320. Okay? Now, in part F, notice n and r are the same. Okay? So, n is equal to 5. That's the number on the left. R is equal to 5. That's the number on the right. So, 5 factorial over 5 minus 5 factorial. Okay, so this is 5 factorial over 0 factorial. Now, here's something important you got to know. 0 factorial is equal to 1. 0 factorial is equal to 1. And this is just 5 times 4 times 3 times 2 times 1, which is equal to 120. Okay. Right, you'll find if you compare the fundamental counting principle to factorials or to permutations, a lot of times you get something that's very, very similar. Okay, but that's how you use that formula. All right, so let's move down here to 7 and 8, and we're still going to use the formula. All right, and in number 7, okay, there are 10 finalists in a figure skating competition. How many ways can gold, silver, and bronze medal be awarded? All right, so first of all, there are 10 total figure skaters, or 10 total items, right? So n is the total number of figure skaters, which is 10. Now, we're going to award 3 places, bronze, silver, and gold, right? So we are taking 3 places at a time, so R is equal to 3, all right? So when we write the permutation formula, it's going to look like this. And on the left, R on the right, and then we plug it in, n factorial over n minus r factorial, which would be 10 factorial over 7 factorial. Okay? All right, and for this one, I mean, you could go to your calculator, all right, and you can go 10 factorial divided by 7 factorial, and it'll do all of that for you, and you will get 720 as your answer. Okay, so there's 720 different ways we can award bronze, silver, and gold. Number 8, something a little similar here. 8 people enter the best pie contest. How many ways can blue, red, and green ribbons be awarded? Right? So this time, n is equal to 8, because I have 8 competitors. We're still awarding 3 places, so r is equal to 3. So we set up our permutations formula, 8, 3, okay? And it's n factorial over n minus r factorial. So that's 8 factorial over 5 factorial. That's going to be 336. So that's permutations. Now, as you turn the page, we are going to shift gears and we're going to now talk about combinations. So with combinations, order does not matter. Okay, with combinations, order does not matter. Some examples of when order doesn't matter is in 11, 12, and 13. In 11, a group of 7 students working on a project need to choose 2 from their group to present the group's report to the class. Doesn't really matter the order you choose the people to present the report. It's 2 of your group. 2 of them are going to go up, they're going to talk, it's over. Order doesn't matter. All right, number 12, 5 cousins at a family reunion decide that 3 of them will go pick up a pizza. All right, that's just a combination. Order doesn't matter. All right, you're just going to choose 3 people to go get the pizza. All right, and then 13, Kelly chooses 3 of 15 flavors of ice cream at the grocery store. Find the number of possibilities. All right, well, order doesn't matter when I'm choosing ice cream flavors. I'm going to choose what I choose and be done with it. Order doesn't matter. I'm not getting any award for it. So as we go through a lot of these permutation and combinations examples, all right, on your homework in the notes, you're going to gradually learn what's a permutation, what's a combination, right, and when to use the appropriate formulas. Okay, so now with combinations, the formula changes. Look at it, it's different. It's n factorial over r factorial times n minus r factorial. Okay, all right, so in this first example right here, okay, if I were to write that out, okay, it would be 8 factorial over 5 factorial times 3 factorial, right? And then I would punch that in my calculator, all right, and you can try that out. You should get 56. Okay, you should get 56, right? All right, so in part G, all right, this would be 7 factorial over 1 factorial times 7 minus 1 factorial. So it's really 7 factorial over 1 factorial times 6 factorial. Right? You do all that work and you get 7. And then finally h, n, and r are the same. So this would be 2 factorial over 2 factorial times 2 minus 2 factorial. Or in other words, 2 factorial over 2 factorial times 0 factorial. Remember, 0 factorial is 1. Right? So you end up finally with the answer of just 2 when all is said and done. Okay? All right, so let's use this formula. Okay? So in number 11, a group of 7 students working on a project needs to choose 2 from their group to present. How many ways can they choose the 2 students? Well, there's 7 students, so that's my n. And we're choosing 2 of them, so r is 2. So 7, 2. So it's 7 factorial over 2 factorial times 7 minus 2 factorial. Or in other words, 7 factorial over 2 factorial times 5 factorial. Okay? 21. Okay. 21 different ways 2 students can present to the class. Okay? All right, in number 12, okay, n is equal to 5, r is equal to 3. 3 of them are going to get the pizza. So it looks like this, 5c3, 5 factorial over 3 factorial, 5 minus 3 factorial. And you get 10. Okay, and then finally, Kelly and the ice cream, 15 flavors, so n is 15. We're choosing how many? 3, so r is 3. So looks like this. So 15 factorial over 3 factorial times 15 minus 3. Final answer here, 455. Have any questions? Let me know.